This is Peter Davis, and this is my contribution for the SM² Statistical Mechanics of Soft Matter meeting for 2020. The title of my talk is Anisotropic Heat Flow in Shearing Fluids, and this work was done with Billy Todd from Swinburne University and Ed Smith from Imperial College, but now at Brunel University. So our motivation is to study heat flow in materials that can become highly anisotropic due to strong shear, for example in polymer melts. And on the right you can see a polymer melt under simple planar shear with a linear velocity profile, and the molecules you see can become aligned, stretched and aligned due to the shear flow, and that leads to anisotropic heat flow in the system. You can also have shear flow driven by an external field, as you see in the lower part of the figure, where you have a polymer solution between two walls that's driven by an external field, and that'll develop a quadratic velocity profile where the strain rate has a curvature. So in the lower case, you can see that you can get a temperature profile that does actually show that there's a temperature gradient across the system. Heat will flow from the center to the walls, and depending on the width of the channel and the strength of the external field, that temperature gradient will vary. So we're going to assume that the heat flux can depend on the temperature gradient, the velocity gradient, and the curvature of the velocity gradient. It requires nonlinear coupling to involve the velocity gradient and the curvature of the velocity gradient. So in the linear regime, you only expect the heat flux to depend on the temperature gradient alone. We're going to assume that we can get the constitutive equation for the heat flux by expanding the heat flux vector in powers of the thermodynamic forces. So we're going to go to first order in the temperature gradient and include combinations of the velocity gradient and the curvature of the velocity gradient, and we'll go up to 6th rank isotropic property tensors, but that simplifies enormously due to the isotropy of the system in the equilibrium state, which is what you're expanding around. And also if you assume a planar velocity field, then things simplify enormously. So with that velocity field, you get the result at the bottom of the slide, which says that the heat flux depends on the temperature gradient with the thermal conductivity tensor, which we call the effective thermal conductivity. And then you have two other terms that depend on the curvature of the velocity field. Now in this presentation, we'll only be talking about a linear velocity profile, so that means that there's no curvature, and we'll ignore the effects of those terms. So our constitutive equation has, in general, has three terms. The effective thermal conductivity tensor has diagonal elements which depend on the square of the strain rate, and off-diagonal elements that go linearly in the strain rate. Because we've got off-diagonal elements, that means that we can get a heat flux component that's not in the direction of the temperature gradient. So the temperature gradient goes from a maximum, or the temperature goes from a maximum, say, in the center of a channel to the walls, a lower temperature at the walls, and heat flow is driven from the center to the walls. But we can get a small component that's in the direction of the flow due to the anisotropy of the thermal conductivity tensor. To evaluate the thermal conductivity tensor components, we need an expression for the heat flux. And what we're going to do is use the volume averaged form of the Irving-Kirkwood heat flux vector. So the exact form of the Irving-Kirkwood heat flux vector looks like this. It's got a kinetic component and a configurational component, and we need to evaluate the delta functions, so we must do some sort of integration. What we do is we average over a small volume delta V to get the volume averaged heat flux. For the kinetic term, that results in integrating the delta function results in a selector function which is equal to 1 for particles that are inside the volume delta V, and it's equal to 0 for particles that are outside that volume. For the configurational part, we have to evaluate a slightly more complicated integral involving the delta function and the streaming velocity. When we do that, what you see is that we end up with a result at the bottom which involves the length of the part of the vector joining particles I and j that are interacting, the length of that line segment that's within the volume V, and we have an average streaming velocity on that part of the vector Rij. So that's the average velocity over that part of the line segment that's in the volume V. To fully evaluate the kinetic part, of course, we have to break it up into the total velocity and streaming velocity components. That leads to a complicated expression, but nevertheless it's possible to do it in computations. And we find that it's best to post-process the results in order to get accurate streaming velocity estimates to use in our heat flux vector. So that involves the average streaming velocity inside the delta V, which is really only available at the end of the run. The same thing applies to the configurational part of the pressure tensor. For practical computation, we use an average streaming velocity over the volume V rather than the average on the line segment that's within delta V, because this is a little bit simpler and the error in making this approximation is very, very small. You can also evaluate the surface averaged heat flux, which is the heat flux going through a little area element delta A. To evaluate that, it's useful to use the divergence theorem. I won't go into the details, but just to say that this actually reduces to the method of planes result when you have an infinite plane. And so you can do the same thing and break up the plane across the simulation region into smaller elements, and you can evaluate the heat flux in small through small area elements. So we have, similarly to the other case, we have an area selector in this case, and a plane selector, and a surface spanning function which tells you whether particles I and j are interacting through the area delta A. So in our simulations, first of all we use simple heat flow by setting up a temperature gradient with no flow to determine the linear thermal conductivity, and then we apply planar shear flow to determine the off-diagonal components or the corrections to the thermal conductivity that are due to the shear. And remember that the curvature of the velocity gradient is negligible in planar shear. We are doing Poisson flow simulations to look at the curvature effects, but we're not including that in this presentation. So in our results, we're just looking at simple WCA particles with the Nose-Hoover thermostat on the walls to generate a temperature gradient. We've got no shear in the first set of simulations and varying the density. In the second set of simulations, we have planar shear with a temperature profile that's generated naturally by the viscous heating of the fluid. And we also vary the density in that case. So that's our system set up. We have walls with a Lennard-Jones type fluid in between, and we can move one wall relative to the other to generate planar shear. So when we have the temperature gradient only, we get heat flow that's normal to the walls, and we can evaluate the kinetic and configurational parts of the heat flux vector independently, and then add them up to get our total heat flux vector. you'll see that the lines represent the volume averaged heat flux, and the points represent the method of planes or surface averaged heat flux, and they agree very well. So we're pretty sure that our algorithm for determining the heat flux vector is correct. When we evaluate the thermal conductivity from those heat flux vectors and the temperature gradient, then we get a result actually even for WCA particles that's in quite good agreement with what you would find for liquid argon over a temperature range. And at the same density we get actually surprisingly good agreement, which confirms the view really that many of the transport properties are mainly determined by the repulsive part of the potential. So when we only have the temperature gradient, then the thermal conductivity depends on the temperature, and again we find that the volume averaged and method of planes results agree very well, and both of those agree quite well with the experimental results, which are the triangles for the three different values of the density. For planar shear, what we find is that there's a rotation of the heat flux vector away from the normal direction, so there's a component in the flow direction. Now we can look at the velocity gradient, which is very, very nicely linear. So we're just moving one wall relative to the other and we get a linear velocity profile. The temperature profile is quadratic, as you'd expect. Our velocity gradient then is approximately constant because the gradient of that velocity profile is almost flat. There's a little bit of wobbling around near the walls due to the packing of particles near the walls. And our temperature gradient is almost linear, which is saying that that temperature profile is almost perfectly quadratic. So the component of the heat flux in the flow direction is small, but it's not negligible. We do actually find a component of the heat flux in the flow direction. And we can also evaluate the larger heat flux that's perpendicular to the flow direction that's taking heat out to the walls. So when we look at the results for the components of the thermal conductivity tensor, you can see that we get in the circles there are the off-diagonal components that are linear in the strain rate, and they are very nicely linear. And then we also have the squares showing the quadratic dependence of the diagonal components of the thermal conductivity tensor. So in conclusion, what we find is that the volume averaged and the method of planes, or the surface averaged results for the heat flux vector, do agree, but the volume average results have better statistics because you're using all of the particles within a little volume delta V to evaluate the heat flux. We can detect the component of heat flow that's parallel to the streamlines, even for a simple fluid, and we'd expect that this might be a stronger effect when you can have a strongly anisotropic fluid like a polymer melt. In planar shear, the anisotropy of the thermal conductivity tensor is due to the distortion of the pair distribution function under shear. And we're now looking at Poisson flow so that we can look at the curvature dependence of the heat flux vector. So thank you for your attention, and I'll be happy to answer questions when we have our question session. Thank you.